Hey everyone! In this video we're going to continue with hypothesis testing, but now instead of hypothesis testing for the mean of a population, given a small sample or a large sample, we are actually testing for population proportions. So what's the same here? Almost everything. You will compare the p-value against the significance level. If the p-value is less than the significance level, we'll reject the null hypothesis. Otherwise, we'll fail to reject the null hypothesis. What's different is a little bit of the setup. Our null and alternative hypotheses will look slightly different. We're going to use p instead of mu because this is a proportion. And the calculation of our p-value is slightly different as well because we're dealing with a different type of data set. So what's actually happening here is these are the p-value, or not the p-value, but the proportion that we're talking about resembles a binomial distribution, a binomial problem, where we have a probability of success, p, and we have a probability of not success, which is q, and then we have the number of items that we are sampling. And so if you remember, when we did a binomial distribution in the last unit, what we would do is we knew that the population, or that the mean was going to be n times p, and the standard deviation was going to be the square root of npq. So what's happening now is when we take a sample from a population, the sampling distribution for the p hat, which is our sampling proportion, it's our sample proportion, which is just the number of values that we got out of the size of the sample that we took, and then the number of values that corresponded with a favorable outcome in that sample, our successes, if you will. So when we take a bunch of samples out of a population and find a sampling proportion for it, it turns out that that sampling distribution is normal as long as n times p is greater than or equal to 5 and n times q is greater than or equal to 5. So then what that means is it's not only normally distributed, but the mean of that distribution is going to be the p-value that we got, or it's going to be the p-value is going to be the claim, and then the standard deviation is going to be the square root of pq divided by n. So this is the standard error for that sampling distribution. So it's the standard deviation for the sampling distribution known as the standard error. Since the sampling distribution p hat is normally distributed, now we can use all the things we've been using all along. We can use our norm.dist function because this is a z-score. This falls on the standard normal curve. So we can use norm.dist, and we're just going to put p hat mu of sub p. So that's the mean of the distribution, and then the mean is standard error, and then of course true because we want the cumulative effect. Our null hypothesis. I want to talk about this in a little bit more detail because it seems like we are struggling a little bit with this, looking at the problem sets, this and what our probability, our p-value is going to be. So the probability, or the null hypothesis, is always going to be that the proportion is the historical thing or the thing we're testing. So it's going to be it's usually the first thing that's brought up in the problem. We'll do an example in a minute, but that's going to be, there's some claim that this is true, and we're going to go along with that claim and say, yeah, maybe it's true. And then based on the sample that we got, what's the probability, that's the alternative hypothesis, what's the probability that this proportion that we got in our alternative hypothesis is far enough away from what the claim is or what the historical average is for us to reject it, or do we not have enough evidence to reject it? So our p-value is always going to be the probability that our p hat is some distance away from p. So again, we want to make sure it's always going to be less than or greater than. We want to make sure that we're always moving away from our historical p-value or the p-value that we're testing, because we're always looking to see if the values we have, if the area is going to compared to the tail of our distribution. So whether it's the left tail or the right tail or both tails, we are always looking for the probability that we are somewhere away from the mean. We don't want to include the mean in our area that we're finding, our probability that we're finding in the curve. So we're going to do 3 examples. We're going to do one in this video, and then we'll do the other 2 in the next video. So a medical researcher claims that less than 20% of adults in the United States are allergic to medication. In a random sample of 100 adults, 15% say they have such an allergy. At the 0.01 significance level, is there enough evidence to support the researcher's claim? So the researcher's claim is the thing that I want to test. And the researcher is saying 20%. Okay? So first, let's make sure we can do a z-test with this information. P in this case is 0.20, because that is the historical claim here. That's the researcher's claim is 0.20, which means that Q is 1 minus 0.2, which is 0.8. N in this case is 100. Let's make sure that 100 times P is greater than 5. And let's make sure that 100 times Q is greater than 5. Since both of these numbers are greater than 5, we can use a z-test with this information. We can continue with this problem. If either of these numbers ended up being less than 5, then I would not be able to continue with the method that I'm showing you. So now, let's write out our null hypothesis. In this case, P equals 0.2. Our alternative hypothesis is going to be based on the fact that the researcher said less than 20%. We got a value that's less than 20%. So our claim, our alternative hypothesis is that P, the proportion is not 0.2, it's actually less than that. And we're trying to figure out if it's significantly, statistically significant enough of a difference for us to say, you know what, it's not 0.2, it's something else. So that's just the mathematical writing of our null and our alternative hypothesis. Next, we're going to move on to our p-value. Now, I don't always break it down like this. I'm breaking it down so that we can remember the steps of going through this problem. But in example 2, I'm just going to say at the whatever significance level, is there enough evidence to support or reject this claim? And you're going to go through all of these steps on your own. So the next thing I need to know is, what is the p-value? So I need to calculate, I know what my x is. In this case, this is p hat. And that is not, that's p hat. Okay. Then I have my mu. In this case, we normally used mu. In this case, that's just p. That's the p-value that we have above. And then we have our standard error. In this case, that's our sigma sub p hat. But that's my standard error. So x is what's given here. In this case, it's 0.15. Mu, or my p-value, is the 0.2 that was part of my claim. So what used to be mu is now p. And then my standard error, I'm going to have to calculate. That's the square root of p times q divided by n. and that gives me 0.04. So once I have my x, my p hat, my p, and my standard error, I can go ahead and find the probability, which is the p-value, the probability that 0.1 or that p would be less than 0.2, or actually 0.15. What's the probability that I'd be less than 0.15? And I'm using a less than because not only was our claim less than, but the value I got for p hat is less than mu. I don't want to do greater than because then I would include p in that calculation. I want to move away from p in this calculation. Same thing that I've been doing all along. So I'm looking for the probability that our p hat would be less than 0.15. So I'm going to use my norm.dist function, and that's going to be this value, comma, this value, comma, standard error, comma, true. And that gives me a value of 0.10564977. Now, since this value is greater than 0.01, which was the significance level that I was using, I am going to fail to reject the null hypothesis. Let's interpret this decision in the context of the original claim. There is not enough evidence to support the claim that less than 20% of adults in the U.S. are allergic to medication. What's the only type of error we could have here? Type 2. In this case, what does that mean? It means we don't think it is less than 20% when it actually is.